All right, let's introduce ourselves to acids. What is an acid? There are a couple different ways of defining an acid. The first way we're going to define an acid is based on the Arrhenius definition of an acid. According to Arrhenius, an acid is anything that increases the hydrogen ion content of water. That means that acids have to have what? If they're going to increase the hydrogen ion content of acids, all acids must have hydrogen, right? In order to be an Arrhenius acid, you have to have a hydrogen. Not only that, but that hydrogen has to be capable of leaving the molecule. Therefore, your clue that something is an acid, or when you're looking at a compound and just trying to decide whether it's an acid or not, your big clue is going to be that hydrogen is generally the first element listed. All right, so let's take a look at your prototypical acid here. Hydrochloric acid. Hydrochloric acid, when placed in water, separates into the hydrogen ion and the chloride ion. All acids follow a pattern. All acids consist of a hydrogen ion and then a rest of the acid. And we always denote this rest of the acid using a capital letter A. The acid will always separate into two parts. One of those two parts will all separate into two parts when dissolved in water. One of those two parts will be a hydrogen ion. Now, hydrogen is just the worst person to break up with, right? Because when hydrogen breaks up with the acid, it leaves its electron behind. So it goes away, and it becomes the hydrogen ion with a positive charge, and it leaves this electron behind. So the rest of the acid, or the acid part that's left behind, also referred to as the conjugate base, has a negative charge. I should have written an A there, right? So what you'll see is an acid will always break up into a hydrogen ion and an anion. This definition, which may, I believe, be the definition given to you by your book, creates a false impression. It says that an acid increases the hydrogen ion content of water. There's a problem with that. What is a hydrogen ion? A hydrogen ion is actually a proton, right? Hydrogen atom only consists of one electron and one proton. So your hydrogen ion is actually a proton, or pure unadulterated negative charge. Pure unadulterated positive charge. So if an acid produces pure unadulterated negative positive charge into the water, what do you think is going to happen? Well, water is a funny molecule. Water has a shape that makes it bent, where it has hydrogen sticking backwards behind the oxygen, kind of like a V, and sticking out in front of the molecule, sort of like antenna on an insect, are two lone pairs of electrons. So you have a molecule in water that has these electrons sticking out here in front. And these electrons have a partial negative charge to them. This partial negative charge is irresistible to this lonely hydrogen ion. This lonely hydrogen ion says, "Holy cow, those are some lonely electrons, and hey, let's face it, I'm pure positive energy, and who can resist me?" The water molecule sure can't. What happens is the water molecule sees that proton and it will actually donate one of its lone pairs of electrons to that hydrogen, to form an ion known H3O+, known as the hydronium ion. Therefore, a better definition of acids is an acid is anything that increases the hydronium ion concentration of water. This attraction of water molecules for that proton in an acid is so great that you'll never in water actually see, or never in water actually find, those protons floating around lonely. They never exist even for a picosecond. Another way to view this acid-base reaction would be you have the anion, you have your water with this lone pairs of electrons sticking out here. And what happens is, as soon as that acid hits the water molecules crowd around, shove a pair of electrons at the hydrogen. The hydrogen says, I like water's electrons better than whoever I'm bonded to. You can keep my electron because water's offering me two that look a lot better. So never in water will you actually find the hydrogen ion. Instead, you'll always find the acid forming the hydronium ion. Therefore, a lot of textbooks simply skip the hydrogen ion part and go straight to the definition as an acid being anything that increases the hydronium ion content of water. Therefore, they'll write the acid reaction as shown here. Let's take a look at the prototypical hydrochloric acid. They'll say hydrochloric acid placed in water produces the hydronium ion and the chloride ion. If you look at this reaction, you'll say, or I've had students say in the past, hey, this reaction isn't balanced, right? After all, I have an oxygen over here as a product, and I don't see it over here as a reactant. Also, I have two extra hydrogens over here that I don't have over here. That oxygen and that extra hydrogen comes from water. We place water over the arrow here instead of on the reactant side because water's ubiquitous, right? We know that we're dealing with an aqueous solution. Plus, we don't want water to be the hero of the reaction. We don't want to focus on water being the participant. What we're really interested in is we're really interested in this molecule and these two molecules, not the water. So we kind of place water out of the way here by placing it over the arrow. And you'll see that done quite a bit in chemistry. We want to tell you something's a reactant, but we don't want you to focus on it, so we'll throw it up here above the arrow. So a generic reaction of an acid would be acid HA, reacts with water to yield the hydronium ion and an anion. That's your general pattern. Alright, now let's look at two broad categories of acids, strong acids and weak acids. Before we go any further, I want you to stop and write down Jean Grey. Stop and write down Jean Grey. Jeangrey. Jean Grey. Hope you're writing down Jean Grey. We divide acids into two categories: strong acids and weak acids. Strong acids are acids that dissociate completely in water. What I mean by dissociate completely in water, I mean is it comes completely apart. If I start off with 1 molar of hydrochloric acid, a strong acid, and no hydronium and no chloride, at the end of my reaction, all my hydrochloric acid will be converted to hydronium and to chloride. I'll have 100% conversion. So a strong acid, my acid reaction goes totally to completion. There are 6 strong acids. You're responsible for knowing these 6 strong acids. Fortunately, you know them already, really. If it's been thrown in somebody's face in a movie, it's a strong acid. You have nitric acid, sulfuric acid, perchloric acid, hydrochloric, hydrobromic, hydroiodic. These 3 you kind of have to memorize, but hopefully if you think about things thrown in people's faces in movies, you've already got these 3 memorized. These 3 are all halogens, right? Hydrogen chloride, hydrogen bromide, hydroiodic acid. Note, there is one halogen not on this list. What acid do we not see on this list? We don't see fluorine, right? Common way I can make you mess up on an exam is hydrofluoric acid is a weak acid. It's not on this list, so it's a weak acid. These 6 acids that you see on this list right here are your only strong acids. I should have written it bigger, but any acid that is not one of these 6, that is not on this list, is what's known as a weak acid. So what is a weak acid? Weak acids are acids that dissociate less than 100%. Not only that, all weak acids exist in a state of what's known as equilibrium. Let's take a look at the weak acid hydrofluoric acid. Hydrofluoric acid, placed in water, forms the hydronium ion and the fluoride ion. However, it doesn't want to do so with a 100% commitment. Weak acids, simply put, are acids with commitment issues. If I start off with 100 molecules of hydrofluoric acid, when my reaction stops, 80% of those hydrofluoric acids will still be together. Only 20 of them will have broken up. Unlike my strong acids, where all of my starting molecules become products, for a weak acid, only some of them do. Not only that, but it's more complicated. Weak acids behave like that nightmare high school couple, or your typical sitcom couple, better yet, right? We all knew in high school that one couple who they were together in the morning, they broke up at night, they were together on Valentine's Day, they broke up the next day, or the guy didn't want to buy a gift, so he broke up the day before Valentine's Day and then got back together the day after, right? One moment they're together, the next moment they're apart, right? Every sitcom has a couple like this, right? Robin and Ted, Robin and Barney, Ross and Rachel. Yes? We all know what we're talking about here. Same way for our hydrochloric acid or our weak acids. Weak acids are constantly breaking up and then getting back together. At the same time that you have some couples breaking up, you have other couples reforming. Because my weak acid is constantly breaking up and getting back together, the arrow for a weak acid reaction takes a funny looking shape. The arrow for a weak acid reaction is a half forward arrow with a very small backwards pointing half arrow underneath it. This arrow shape is used to denote a state known as dynamic equilibrium. And what that means is that you have a forward reaction and a backwards reaction occurring at the same time. However, your system or your reaction eventually reaches a state where the number of couples breaking up equals the number of couples getting back together. And while the molecules that are together or breaking up is constantly changing, the ratio of couples broken up to the ratio of the couples still together is constant. When this situation occurs, it's known as dynamic equilibrium. So for my weak acid here, I have molecules breaking up and I have molecules getting back together. However, if I sampled the population at any given time, what I discover is that I always have 80 molecules together and I always have 20 molecules broken up. What 20 molecules are together and what 80 molecules are broken up would be different, but my ratio of those molecules broken up to those together would never waver from 20 to 80. When this situation occurs, my system has reached what's known as dynamic equilibrium. And next semester, more than half the chapters actually deal with mathematically examining equilibrium and the effects of equilibrium. All you need to know right now is that weak acids exist in this dynamic equilibrium, and as a result of this dynamic equilibrium, at any given period of time, you're going to find some of your acid molecules together and some of them apart. In other words, your weak acids dissociate at less than 100%. Someone who never gives less than 100% is Olivia Munn in her portrayal of Psylocke. Why don't you write down Psylocke? P-S-Y-L-O-C-K-E. Psylocke. Apparently the theme for today is Psychic X-Men. Psylocke. One thing you have to be able to do is you have to be able to write an equation for an acid. Writing an equation for an acid is pretty easy. Couple quick things in terms of terminology, though. When you have an acid, you're removing a proton from the acid. Because you're removing a proton, that means you're leaving an electron behind. So whatever's left behind is going to have a negative charge. This negatively charged anion is referred to as a conjugate base. The other product of your acid dissociation reaction is always going to be the hydronium ion. So an acid dissociation reaction will produce a hydronium ion and an anion. Let's look at this in a stepwise fashion. You're told to write the equation for the dissociation of acetic acid. In an acid reaction, you are removing a hydrogen, leaving the anion behind. So the first thing you do in writing the reaction is you write the acid on the reactant side. So we've got acetic acid. Remember, by convention, you always list an acid as being in the aqueous phase. On the product side, you're going to write the hydronium ion, again in the aqueous phase. And then you're going to write the conjugate base, or the anion. So what you do is you take your acid. To determine your conjugate base, you take your acid, you remove the hydrogen from it, and you add a negative sign. So if I remove a hydrogen, I'm left with my acetate ion. Sorry, my handwriting got really sloppy there because I was trying to write too small. Your acetate ion, again in the aqueous phase. Now the last thing you have to do is you have to add your arrow. If you have a strong acid, you draw a one-way arrow. If you have a weak acid, you draw your double-headed arrow, and then you write water above it. We have a weak acid. Why? Because acetic acid isn't one of those 6 strong acids that you've had to memorize. So I'm going to draw my double-headed arrow, and I'm going to write water up above it. And that's how you write the acid dissociation reaction. Okay, how about you try one? Okay, you know the drill here. Pause me and try this on your own. All right. Hopefully that wasn't one of those long, awkward pauses like I often experience on dates, but one of those rather comfortable silence pauses that you experienced as you worked this problem. Write the equation for the dissociation of nitric acid. Write the acid on the reactant side. Should always be in the aqueous phase. Then, on the reactant side, write the hydronium ion. Then write the conjugate base. Remember, you always figure out the conjugate base by taking your acid, removing the hydrogen, adding a negative sign. So when you remove the hydrogen, you're left with the nitrate ion. Now we need to determine our arrow. Nitric acid is a strong acid. It's one of the 6 acids you've memorized. So you simply write a regular arrow and you place water above it. And there's your acid dissociation reaction. Let's look at a special case of acids known as polyprotic acids. Polyprotic acids are acids that have more than one hydrogen they can lose. You'll know you have a polyprotic acid when once again you have hydrogen as your first element. However, you'll have more than one of those hydrogens as the first element. For example, sulfurous acid, you have 2 hydrogens. Sulfuric acid, you have 2 hydrogens. Phosphoric acid, you have 3 hydrogens. The important thing to remember when it comes to polyprotic acids is that polyprotic acids can only lose 1 hydrogen at a time. Let's take a look at what I'm talking about. The temptation is to say, all right, I have sulfurous acid here. It's got 2 hydrogens, so I bet it's going to do this. That's an AQ down there, that chicken scratch. The temptation is to say that this is going to occur. And a lot of people will try to put on exams that this is what occurs. That's wrong. That doesn't occur. That does not happen. Your sulfurous acid won't lose 2 hydrogens at once. Instead, it loses 1 at a time. Let's take a look at what really does happen for sulfurous acid. if I have sulfurous acid, it's going to start off behaving like a normal acid. I'm a little too close to the edge there. There we go. And it's going to lose its first hydrogen. Some of the molecules will lose its first hydrogen and form hydronium. And we're only going to remove that first hydrogen. Now, the removal of this first hydrogen does two things. It creates hydronium, and it creates the bisulfate ion. Now, the bisulfate ion is an acid. Because it has a hydrogen, it can lose two. So, this bisulfate ion can function as a weak acid, and it too can lose a hydrogen and acts as an acid. However, it's going to be much more difficult for bisulfate to lose its hydrogen than it was for the sulfurous acid molecule. Why is that? Well, remember, we're not removing a hydrogen. We're removing a hydrogen ion. We're removing a positively charged particle. What charge does our weak acid have at the moment? Now that we removed that first hydrogen, what charge does it have? It has a negative charge, right? So it's going to be much more difficult for this positive ion to leave the negative ion. I kind of like to think of polyprotic acids kind of like that. Well, let's first do the math here, and then we'll do the conceptual. Most polyprotic acids will lose with a great deal of, will fairly easily lose that first hydrogen. It'll be much more difficult for them, however, to lose the second hydrogen. If we start off the process with 100 molecules of sulfurous acid, then at our endpoint, or at our equilibrium, let's be generous here because sulfurous is fairly strong, 50% of them have broken up to form hydronium and the bisulfite ion. Well, of those 50 bisulfate ions, not all of them are going to want to break up. Of those 50, 40 of them may stay together and only 10 of them will break up. So if we looked at our movements in terms of if we looked at our ratios and our reaction in terms of just our starting material up here, very little of our starting material wound up becoming that. In this little mock-up scenario, I've only got 10% going there. In reality, it would be much, much less than 10%. We're talking 1% or less, really. Very, very small amount, with the exception of a few freak molecules here. It's much, much harder to remove that second hydrogen ion. I like to think of it like this. Sulfide here is a guy who's dating two girls. What happens when those two girls find out about each other? One of them is out of here. One of them is saying, so long, you're an evil son of a gun, I'm never going to have anything to do with you again, right? But then another one says, oh good, that one's gone, now I've got the sulfide ion all to myself. So once it's gotten rid of the other hydrogen ion, it's going to stick around for a while. Yes? See what I'm saying? So it's much easier for your polyprotic acids to lose one hydrogen, much more difficult for it to lose the second. What does that mean, though, in terms of practical applications? What that means is that when you're asked to write the dissociation reaction for a polyprotic acid, you're only going to write that first dissociation. There is some effect from that second dissociation, but we'll deal with that next semester. But for the meantime, when you're faced with a polyprotic acid, you're going to think of the removal of just one of those protons. Just like a polyprotic acid only wants to remove one hydrogen, Cyclops looks like he has one eye when he's wearing his visor. He has two eyes really, but he wears that visor and it looks like he has one, and that's why they call him Cyclops. Why don't you write down Cyclops? C-Y-C-L-O-P-S. Cyclops. All right, polyprotic acids, your turn. Write the dissociation reaction for carbonic acid. All right, hopefully you paused me and wrote this. You treat a polyprotic acid like you would a typical acid. Carbonic acid isn't one of your acids you've memorized, therefore it's a weak acid, so it gets a double-headed arrow with water on top of it. You have the hydronium ion, then you've removed that one hydrogen, so you get the bicarbonate ion, again in the aqueous phase. Chemistry's easy, life is hard, yes? That's the acid dissociation reaction for carbonic acid. How is being a chemist like being in a heavy metal band? Because you're dropping the bass either way. Which, coincidentally enough, brings us to the next topic of conversation, Arrhenius bases. An Arrhenius base is any substance that increases the hydroxide ion concentration of water. In case you've forgotten, OH negative is the hydroxide ion. Your typical Arrhenius base reaction consists of a base, often a solid, placed in water to yield a cation. Acids yielded an anion. For bases, we're getting a cation, and I can't spell today. And a hydroxide ion. Now, bases are kind of scary when we look at their generic reaction. Boo! Hot, get it? Kind of scary? You always form a cation because this cation is going to give its electron to the hydroxide and the hydroxide ion. There are only a few Arrhenius bases you need to be aware of. There are 6 strong Arrhenius bases. Just like strong acids, these strong bases dissociate 100% in water. They also form a pattern on the periodic chart. You have lithium, sodium, potassium, and then potassium swings over to calcium, strontium, and barium. So if you look at your periodic table, you'll find they form a nice little Tetris piece for you here. Lithium, sodium, potassium, calcium, strontium, and barium. Now, these strong bases do dissociate 100%. An important note, considering we just got a lot of time discussing polyprotic acids, strong bases, unlike polyprotic acids, do produce 2 hydroxides. These strong bases right here with 2 hydroxides do produce 2 hydroxides. For example, if I was to write the dissociation reaction for calcium hydroxide, I place my calcium hydroxide in water, and I get the calcium ion plus 2 hydroxides, because I have 2 hydroxides there. So be aware that when you place calcium hydroxide, strontium hydroxide, or barium hydroxide in water, you are going to get 2 hydroxide units out. All right, let's look at some of the fun reactions of acids and bases. All right, let's talk about writing the reaction between Arrhenius acids and Arrhenius bases. They always follow a pattern. The pattern always consists of the acid and the base forming water and a salt. Where does this come from? Well, let's deal with the water first. Your acid is always giving up a hydrogen. Your base is always giving up a hydroxide. That reaction of the hydrogen ion with the hydroxide produces a water. So that's where our water comes from. How about our salt? Well, first of all, a salt is just a fancy way of saying an ionic compound. Whenever, we're not talking table salt here, obviously, although table salt is an example of a salt and a ionic compound. A salt is just a generic way or a fancy way of talking about an ionic compound. We've already mentioned that when the hydrogen leaves the acid, it leaves behind an anion. It leaves behind an anion. So our hydrofluoric acid leaves behind the anion fluoride. Whenever a base reacts, it leaves behind a cation. Well, whenever you have a cation and an anion, you get a ionic compound, which we refer to as a salt. So that's where everything's coming from. Let's take a look at predictive chemistry here. And let's write the reaction that you'd experience between sodium hydroxide and nitric acid. First step's pretty easy. You're just going to write the acids and the bases as reactants. So I've got, and it doesn't matter which one you write first. And that's an AQ for aqueous there, by the way. Hopefully by now you realize that those unintelligible squiggles right there are aqueous. Next thing you need to do is you need to identify the cation from the base. You identify the cation from the base by whatever's not part of the whatever isn't part of the hydroxide is part of the cation. So our cation is going to be sodium, which we know has a +1 charge. Identify the anion from the base. We looked at doing that earlier today. So we remove that hydrogen, add the negative sign. So we've got nitrate and we have sodium. Make a salt from the cation and the anion. Sodium's +1, nitrate's -1, so it'll be a 1-to-1 ratio. Cation always goes first, remember. So we'd have sodium nitrate. Now we're going to write the water and the salt. So we're going to write water. And water is going to be in the liquid phase, not the aqueous phase. That's a lowercase letter L there, right? Water's in the liquid phase. And we'd have sodium nitrate in the aqueous phase. There's a 3 there. And that's all there is to it. Now let's have you try one. Oh, whoops. Got ahead of myself here. Before you try one, let's do one more here. This is going to be a little bit different than normal. We're dealing with a polyprotic acid here. You have to form 1 water for every acidic hydrogen you have, or 1 water for every hydroxide you have. In this case, we have a polyprotic acid, so we're going to have 2 hydrogens to deal with. So our process is going to stay the same. We're going to write our base, and we're going to write our acid. We're going to identify our cation, sodium. We're going to identify our base. Our base, we're going to remove both protons. So if we're removing 2 protons, we're left with the carbonate ion. right? We have H2CO3. I'm removing 2 hydrogens, so I'm leaving 2 electrons abandoned. To form a salt from these two, I'm going to need 2 sodiums to counteract the -2 charge on my carbonate. So my salt would be Na2CO3. Let your nomenclature rules and your charge dictate your salt, right? I didn't look at my equation and say I have 1 sodium and 1 carbonate. No, I said I've got a -2 charge on my carbonate, so I need 2 sodiums to balance it out. Then I have water. I have 2 hydrogens I'm moving, so I'm forming 2 waters. And my water is, of course, in the liquid phase. Then I have 2 sodiums in my equation, so I need to balance by placing a 2 in front of my hydroxide. That also gives me 2 hydroxides to react with my 2 hydrogens, and everything's balanced. Now let's have you try one. Pause me and try this on your own. All right. Hopefully you paused me here. And you're saying, really, stretch this thing out more. We've been listening to you for close to 2 hours now. I know, aren't you lucky? At any rate, write your acid and your base. I've got calcium hydroxide, and I have, aqueous, and I have hydrogen bromide, aqueous. I know I'm going to form water. How many waters am I going to form? Well, I have 2 hydroxides here, right? So that means in my overall equation, I'm going to wind up forming 2 water molecules, pardon me. I need to form my salt, so I'm going to identify my cation, calcium, 2+. My anion is going to be bromide. I'm going to need 2 bromines to counterbalance the charge on my calcium, so my salt would wind up being calcium bromide. And that's going to be aqueous. Check to see if I'm balanced. Oh, hey, I need 2 hydrobromic acid molecules to balance out my bromines and to provide enough hydrogens to form my water molecules. And there you are. Beep. All right. Let's now take a look at let's now view acid-base reactions through the lens of ionic equations. To write the ionic equation for strong acid reactions, we treat it just like we would a precipitation reaction. So step 1, we're going to write our ions. All your strong bases are ionic compounds. So we know that they dissociate completely. Strong acids also dissociate completely. Here's where the difference occurs. What happens when an acid dissociates? Does it form the hydrogen ion? No, it forms the hydronium ion. And the iodide ion. Then, I'm not going to crowd things. We write our products. We have water. Is water an ionic compound? No, water is not an ionic compound. Water is a covalent compound. Not only that, but it's in the liquid form. So we don't break water up. Water stays together as a liquid. We have sodium iodide. So sodium iodide is going to break up. Because it's an ionic compound and it's aqueous. So there's our ionic compound. Now, there's our ionic equation. And if we look at that ionic equation, what do we notice? We notice we have a couple spectator ions there, right? Sodium appears the sodium ion appears as a reactant, and it appears the exact same way as a product. Same for the iodide ion. So we can cross those out, and when we do, we're left with a net ionic equation, and our net ionic equation tells us that hydroxide ion plus the hydronium ion yields water, and we need to balance. There we go. So there's our net ionic equation. For any strong acid or strong base, for any strong acid, strong base reaction, the net ionic equation will always be that. For any strong acid, strong base reaction, the net ionic equation will always be hydroxide plus hydronium yields 2 water molecules. You should write that down and make a note of it, just like you should write down apocalypse. A-P-O-C-A-L-Y-P-S-E. Write down apocalypse. And just in case you had trouble with my chicken scratch there, for strong acids, strong bases, the net ionic equation is always going to be the hydronium ion plus the hydroxide ion equals water, or if you don't want to view it from the standpoint of hydronium, the hydrogen ion plus hydroxide ion yields water. That's always the net ionic equation for strong acid, strong base. What about weak acids and weak bases? Weak acids do not dissociate completely in water. Therefore, when you're writing an ionic equation, you don't break them up. Let's take a look at an example. Write the ionic equation for the reaction of hydrofluoric acid and potassium hydroxide. When writing an ionic equation, your first step is to break aqueous ionic compounds and strong acids into their ions. You never break anything else apart. All right, so we're looking at figuring out the ionic equation for the reaction between hydrofluoric acid and potassium hydroxide. We know that because you're reacting an acid and a base, you're going to get water as one of your products. The other product is going to be, you have the potassium ion and the fluoride ion 1-to-1. And it contains a group 1A anion, a group 1A cation, so it's going to be soluble in water. So we're going to break up aqueous ionic compounds. The first compound we come to is hydrofluoric acid. Is hydrofluoric acid a strong acid? No, it's a weak acid. Is it an ionic compound? No. Therefore, we don't break it up. Then we come to potassium hydroxide. Potassium hydroxide is an ionic compound. It's got a metal as the first element, yes? So we break it up. Our products, we have water. Water is a covalent compound, so it stays together. Then we have potassium fluoride. It's aqueous, so it gets broken up. Balanced, everything's balanced. So there's our ionic equation. If we wanted to do a net ionic equation, who's our only spectator? If you look, we only have one spectator ion in this reaction. The only thing that appears the same on both sides of the equation is the potassium ion. So our net ionic equation really wouldn't look that different than our ionic equation. And that would be our net ionic equation right there. I will tell you right now, this is a favorite test bank question. Test banks love doing this sort of thing. They love asking you these weak acids. Make sure that you never split up a weak acid. In an ionic equation, weak acids are written together like that. Now let's have you try one. Pause me. All right. My wife just commented that she really wished she had that ability. But at any rate, you're asked to write the ionic equation for the reaction between acetic acid and calcium hydroxide. First thing you need to do is you need to write the equation itself. I write the molecular equation first. So you have acetic acid. Why did I give myself acetic acid to write with a stylus? Your products are going to be 2 waters because you have 2 hydroxides. And you've got calcium with a 2+, acetate with a -1, so you're going to need 2 acetates to counteract the calcium. And anything with acetate's aqueous. And to balance, you're going to need 2 of them. All right, so there's our molecular equation. Now we're writing the ionic equation. You break up ionic compounds and strong acids only. Acetic acid isn't a strong acid, so we keep acetic acid together. Calcium hydroxide is an ionic compound because it starts with the metal calcium. So you do break it up. Don't go inventing polyatomic ions. You have 2 hydroxides, not some new polyatomic ion you're tempted to make up. All right, now we go to the other side of the arrow. We have water. Water doesn't get broken up. Calcium acetate, however, is an ionic compound, and it's soluble, so it does get broken up. And that's the aqueous sign there. I'm scribbling into the margins. So there's your ionic equation. I balanced as we went along. Your weak acids stay together. Weak acids stay together. Bases, because Arrhenius bases are ionic compounds, get split up. So there's your ionic equation. If we were wanting to do the net equation, who's our only spectator? Calcium is the only spectator. So if we were to write the net ionic equation, the net ionic equation would be, bye-bye calcium, would be the balancing here is going to be a little bit fun. Look at our balancing when we write that net ionic equation. Look at the net ionic equation. We've got 2's in front of everything. What would your math teacher tell you to do? Get rid of the 2's, and she'd be absolutely right. So we actually need to get rid of all those 2's there when it comes to writing the net ionic equation. So your net ionic would simply be acetic acid aqueous plus hydroxide aqueous yields water liquid plus the acetate ion. And I hate styluses. I don't want to raise a storm about it, but you should. Write down storm, S-T-O-R-M, storm. Another example, just to make sure the horse is completely dead, write the net ionic equation for the reaction of hydrocyanic acid and lithium hydroxide. Go. All right. Hopefully you paused me and worked it out on your own. Once again, you're starting by writing the molecular equation for it. We've got hydrocyanic acid. And yeah, I know all the other times I've written the base first. It doesn't matter which one goes first. One of my products is always water. Then I have lithium plus 1, cyanide plus 1, a negative 1, so it'd be lithium cyanide aqueous. We know it's aqueous because the lithium's in group 1, and anything with a group 1A element's aqueous. So to write the ionic equation, we keep our weak acid together. We break apart our base because it's an ionic compound. Water stays together. Our ionic compound breaks up, so there's our ionic equation. Who's our spectator ion? Lithium. Lithium appears the same on both sides of the equation, so bye-bye, lithium. And that gives us a net ionic equation, which is what the problem was asking for, of cyanide plus hydroxide aqueous yields H2O liquid plus the cyanide ion. That's an N there. People say my N's look like W's. There we go. Aqueous. So there's your net ionic equation. Here's another one. Let's see if I can trick you. I'm pausing, letting you try it on your own. All right, are you back? Before you do anything, I hope you realize that nitric acid is one of your strong acids. Lithium hydroxide is a strong base. And whenever you have a strong acid reacting with a strong base, your net ionic equation is always the reaction of hydronium and hydroxide to yield liquid water. Boom! Nailed it. Seriously, watch out for these type of questions when you deal with standardized test banks in particular. They're trying to get you to waste time by doing it the hard way instead of recognizing you have strong acid, strong base.